Okay, we will start in 2 minutes. Good afternoon all. Okay, we will start. So continuing with the previous point, today we will start with the forces on image body. Next point. So last lecture we saw some problems. Then next point comes, which is called as a pressure drag and friction drag. Just a minute. Yes. The next point, pressure drag and friction drag. Friction drag. So we saw the equation. FD is equal to integration P cos theta into dA plus integration tau 0 sin theta dA. In this equation, the first part and second part. The first part is known as a pressure drag. And second part is known as a friction drag. Here, the relative means if we consider the contribution for the pressure drag and friction drag, the total drag depends upon this total drag is depending upon the shape of material, shape of body, that is immersed body, then position of that body in the flow, position, first shape, second position, and third fluid properties, means like a density and viscosity. So what we will do for that, we will consider a flow over a plate. There is one plate over which fluid is flowing with uniform velocity u. And that plate is assumed to be flat plate. And it is in the parallel to the direction of flow. In this case, cos theta, what will be the value of cos theta? And what you will find, it is like this, means shear stress will act like this, tau 0. So in this case, what will be the value of cos theta? One second. Yes, what will be the value of cos theta? When flat plate is in parallel with the flow. Answer is simple. Cos theta, which is nothing but angle made by pressure with the direction of motion, here it is 90 degree. Theta is 90 degree. So the term in above equation, integration P cos theta dA will be integration P cos 90 degree dA, which is nothing but 0. Hence, total drag will be equal to friction drag. So here, the drag which is happening is total drag is due to friction only. Only friction is responsible in that case. The term which is nothing but integration tau 0 sine theta dA will become main, that is FD. It will be responsible for generating the total drag. Then if we do the opposite condition means what? If we do opposite to that, means flow is like this. On this flow, we are keeping the plate now perpendicular, complete. So what will happen? Flow will come from this side and it will move like this. And in this region, some sort of eddies will generate. So what will happen? Flow will be, some is moving in that direction, some is moving in this direction, and there is responsible tau. And here there is a separation point. So in this second condition, what will happen? The angle made by pressure with the direction of motion will be 0. Theta is here 0. So if angle is theta is 0, then term P P cos theta dA will be also having maximum value, that is ABD. Why it is so? Because integration tau 0 sine 0 dA will be equal to, here sine 0 will be equal to 0. That is nothing but angle made with the direction of motion is 0, so that friction drag will become 0. And total drag will be equal to the pressure difference between the upstream and downstream plate. If the plate is held at angle anything other than 90 or 0, then it will be a combination of both. And total drag will be dependent on pressure drag and friction drag. These two conditions you should remember from the point of exam. That is nothing but pressure drag and friction drag. Only friction drag will happen when plate is in the direction of flow. Only pressure drag will occur when plate is kept in the direction perpendicular to the flow. Plate is perpendicular to flow, whole pressure will be acted on the surface of that plate. So that is the concept of pressure drag and friction drag. Then comes the concept of streamline body. Many times we have used this word streamline body. So streamline body, if we consider, it is nothing but body whose surface coincides with the streamlines when body is placed in the flow. All the edges of the bodies should be coinciding with the streamlines of the flow. In that case, what will happen? Separation of flow will take place only at the rearmost part of a body. So boundary layer separation will not happen in those streamline bodies. The body layer will be start at the, means whatever boundary layer is there, that will start at the leading edge and become turbulent from laminar, as we know the formation of boundary layer, but it will not separate at the rearmost part of the body in case of streamline body. Every streamline body, there is a wake formation. Weak formation means where the eddies are forming, that area is very, very small. Then stream body, if we consider, when the total drag on streamline body will be only the friction drag. It will be having same properties as we saw here. The pressure drag is almost negligible. So when we place that particular position, flow may be may not be placed another position. So that is the concept of streamline body. Opposite to that means if we want to take example of streamline body, you can consider this one. Just a minute. So it is the same. This is the example of streamline body. So this body surface is having its boundary parallel to the streamlines of a flow. Opposite to this streamline body, there is a bluff body. Bluff body. Bluff body, it is exactly opposite, so that with the example we can see what is meant by bluff body. So here is the bluff body. So bluff body means what? Whose surface does not coincide with the streamline when it is placed in the flow. The flow is separated from the surface of the body much ahead of the trailing edge, which results in very large weak formation zone. Here you can see, here everywhere weaks are generated. EDs are formed. When drag due to pressure is very less as compared to the drag due to friction. Means large case here pressure, 1 second. Hello. So when there is a pressure drag maximum, bluff body is there. When pressure drag is minimum, we can say it is a streamline body. In a bluff body, such shape in which pressure drag is very large as compared to the friction lag, called as a bluff body. So with this bluff body structure, which is not recommended when we consider the flow has to be streamlined, or when we consider the aerodynamic designs, in that case, we are not recommending the bluff bodies. So you can give the examples. Just a minute. Wait a minute. I'm trying to find one video. Okay. So bluff bodies and streamline bodies, with respect to that pressure drag and friction drag, everything you have to remember from the point of view as a write a short note on based on that. Then it comes to the last point of this forces on image body. which is called as a drag formation on streamline body. So for that, what we will consider, there is one cylinder or aerofoil shape. From base point of that, what you have to remember, the concept of one, which is called as a Magnus effect. Most of the time, it is also asked related with this Magnus effect. Means how it is defined. First, I will tell the definition. So what is mean by this? There is a cylinder, and that cylinder is rotated in uniform flow. We know type of flow, uniform flow. So what will happen? It will result in lift force. And this phenomena of lift force produced by rotating a cylinder in uniform flow is known as a Magnus effect. It is known as Magnus effect. And it is used for different generation, different concepts which are further utilized in the aerodynamics and flight mechanics also. So the definition which you have to remember is Magnus effect. It is simple one. A cylinder is rotated in uniform flow. Lift force is produced on the cylinder. This phenomena of lift force produced by rotating cylinder in uniform flow is known as a Magnus effect. Based on Magnus effect, what we are considering development of lift on an aerofoil. Development of lift. So it is a simple concept. There is two shape. There is one shape of aerofoil, and there is another some weird shape of aerofoil. So both are placed in the uniform flow. It is like this. Its center is I will draw once again. So here it is a symmetrical one, and it is not symmetrical like this. It is like center is passing through it. So both are placed in the uniform flow. Though aerofoil is nothing but it is measured by the length between these. It is called as a chord length. CHORD chord length. And it is denoted by C. And it has angle of attack. Means if we consider the 3D diagram, if suppose this is a symmetrical aerofoil in the 3D shape, 3-dimension shape, then what will happen if suppose it is making some angle with horizontal, that angle is alpha, it is called as the angle of attack, and this length which is called as a L, it is nothing but span. So what you remember, chord angle of attack and span of a aerofoil. It is denoted by C, it is denoted by alpha, and it is denoted by L. So what will happen? The drag force on the aerofoil is always small due to the design of the body, which is already streamline body. So what will happen due to the theoretical analysis? Some circulation will generate. In that case, what we are considering, when we are having such type of aerofoil, when it will be having some special kind of angle of attack, then we will get a lift of some quantity. So it will totally depend on the angle of angle of attack at which it is kept, and based on that what will be the length, chord length, and how we are rotating this upper. Suppose it is fixed to this center, then how, at what way you are rotating that aerofoil. Based on that, the lift on that aerofoil is dependent. Also it depends on whether the aerofoil is symmetrical or not. So when flying object, like example of aeroplane, it is taken, the weight of aeroplane is equal to the lift force and the thrust developed by the engine. So there are some formulas which are not required for us. We have to remember all these things as a theoretical part, as an introductory part, how the lift is generated and how, on what factors development of lift on aerofoil is defined. So today, for this forces on human body, as a last part, we saw pressure drag means what, friction drag means what, blob body means what, and streamline body means what, Magnus effect is what, and development of lift on aerofoil means what. All these points we have seen for today's session. Now, continuing with this, for the next part, that is not, unfortunately, it was not mentioned in our syllabus. That part is again from the point of exam is important, and it is not printed by mistake, and that is the second part of this unit. And again, it is a small part, although it is important. It is within 2 lectures we will finish that part also. It is a compressible flow. The unit number 5, part number 2 is nothing but compressible flow. So I will start with that point. Compressible flow. Compressible flow is nothing but the flow which is having density not constant. Means the density of flow, if we measure at different points, you may find that it is having different density. During the flow, point to point or section to section, density may change. The density changes from point to point in a compressible flow. And in case of an incompressible flow, density of fluid is constant. So up till now, we have everywhere assumed that flow is incompressible right from first unit, like from all the definitions related with Bernoulli's theorem and kinematics of fluid flow. Everywhere we have considered flow is incompressible. The basic equations which we have seen, like continuity equation, Bernoulli's equation, momentum equation, all were dependent on the assumption that fluid is incompressible. This assumption is only for liquids, as liquids are incompressible. We know we can't compress the liquid. It is not possible to make 1 liter of water half liter by compressing. So that example you should remember. So liquids are incompressible. So this chapter is only for related to gases. All gases, like flow of gases to orifice, flow of gases to nozzles, flow of gases in machines like compressors, gas turbines, everywhere, or projection in aeroplane flying in the high altitude with high velocity and density of fluid changes during the flow. The change in density of a fluid is nothing but change in pressure and temperature. So what we have to consider, the thermodynamic behavior we should obey or we should consider in that case. Means this compressible flow is totally applicable for gases only dependent on gases. Means whatever derivations we have seen, all derivations we have to reconstruct for such type of a compressible flow. So today we will see the concept of thermodynamic relations from the chapter number 1. That is, first is the equation of state. Equation of state. You should remember everything from the point of theory. I will give the book special cuttings from the books, and which are important one from the compressible point of view. Here equation of state is nothing but equation which gives the relationship between pressure, temperature and specific volume of a gas. So you know this perfect gas equation. Most of the times you might have used PV is equal to RT, where you know P is the pressure, V is the volume, T is the temperature, which is in Kelvin, that is 273 plus degrees Celsius. Then R is gas constant. This you might have used in the 12th, and which is nothing but 287 joule kg per Kelvin of a air. So here V is specific volume. V is nothing but specific volume, and we generally denote by upstairs U, like upstairs C. So it is nothing but specific volume. We have already defined specific volume is nothing but 1 by rho. So what you will get the answer, P by rho is equal to RT. That will be the simplification as per our requirement. Then compress means if we have a compressible gas, then the expression or perfect gas, if we take the pressure, temperature and density, all are changing. The change in pressure, change in temperature and density of gas by different processes. You might have learned these things in thermodynamics, which is nothing but isothermal process. What is meant by isothermal process? Anyone?
Temperature remains constant.
So the isothermal process with gas is compressed, means with related to this gas we are compressing, and if we are compressing and expanding, this during this process temperature is remaining constant. Compression, expansion, compression if we follow, then isothermal process, it obeys the Boyle's law. PV is equal to constant. So in other words, P by rho is constant. V is being the specific volume. So this is isothermal process. Then second comes adiabatic. Adiabatic process means what? What will happen in the adiabatic process? Bola. Adiabatic process. Anyone?
Sir, it is the irreversible process.
Okay, but main irreversible, what is remaining constant? What is remaining constant in adiabatic process? In adiabatic process, what happens when there is a compression or expansion of gas? There is neither process of giving heat or no heat is taken from the surrounding, and it is nothing but PV raised to K is constant. So nothing but K is nothing but Cp upon Cv, and in general it is 1.4. So we can rewrite the equation P by rho is constant. Rho raised to K, sorry. P by rho is raised to K. So such type of adiabatic process we are considering. Then there are basic 4 equations of compressible flow. So first is the continuity equation. Continuity equation, which we saw in our second unit, that it is based on the law of conversion of mass, which states that matter cannot be created or destroyed. In other words, matter or mass is constant. For one-dimensional steady flow, mass of flow per second is, we know, rho into A into V. Means it is nothing but mass flow rate. Lot many times we saw Q in rho into Q means mass flow rate. So where rho is the density, A is the cross-section area, V is the velocity. So what will happen, as the mass or mass per second is constant, rho AV is remaining constant. This is the first consideration. If we take the derivative, taking the derivative, rho AV, it will become 0 because other side is constant. And if we consider overall, then that is left side. So what you will get, rho is constant. Here we consider first, that is nothing but D into AV plus, keeping AV as a constant, D into rho. Chain rule if we apply. Then what will happen? if we consider the next step, that is further considering the constants, rho dAV is nothing but AdV plus VdA. Again applying the chain rule. So here AV d rho is equal to 0. So altogether what we will get, rho A dV plus rho V dA plus AV to d rho is equal to constant. So if we divide everything by rho AV, then what you will get, dV by V plus dA by A plus d rho by rho is equal to 0, and this is called as a continuity equation for differential form. So it is a continuity equation in the differential form for compressible fluid. Simple. Then second comes Bernoulli's equation. Bernoulli's equation. So Bernoulli's equation we have derived for the compressible flow in previous unit. The same procedure is followed. A flow of fluid particle along streamline in the direction S is considered, and we have derived the Euler's equation, the resistant force on the particle in the direction S of the mass, and what we will get the continuity equation, Euler's equation as dou P by rho plus V dV plus G dZ is equal to 0 as a Euler's equation. Euler's equation that we have obtained already. Then we integrated it and we got the equation as Bernoulli's equation. So what we are doing, we are taking the integration of all these things, and we are getting here constant, and that was our Bernoulli's equation. In other words, what will happen here for the incompressible flow, I will keep dou, because here rho is there. Other things will be integration V dV will be V square by 2 plus GZ is equal to constant. I have not touched the dou P by rho because in case of compressible flow, density is constant. So we can convert this dou P by rho as P by rho for incompressible flow. But in case of compressible flow, density is not constant now. Hence, density cannot be taken outside the integration sign. With change in density, pressure also changes in case of compressible flow. Means what is happening? P and rho both are variables. So the change of rho and change of P is taking place depending upon the type of process during the compressible flow. The value of rho in this equation in the terms of P is obtained and substituted in the equation dou P by rho in the integration form. It will be different in isothermal process and it will be different for adiabatic process. How it is? Let's see. So first, isothermal. If we consider isothermal process. In that isothermal process, P by rho, as we know, is constant. Let's say it is C1. So rho is equal to what? P by C1. Then integration dou P by rho will be equal to integration dou P divided by P upon C1. So it will be nothing but C1 dP by rho. Sorry, C1 dP by P, which is equal to C1 integration dou P by P. So dou P by P, what is the integration? C1 log to the base E P is equal to P upon rho log P. So why it is so? C1 is nothing but P by rho, which is considered here. So just putting back C1 here, you will get as a value P by rho log to the base E P. So what you will get, the Bernoulli's equation, P upon rho log to the base E P plus V square by 2 plus Gz is equal to constant. So let's divide by G everywhere. So we will get P by rho G log to the base E P plus V square by 2G plus Z is equal to constant. So this is the Bernoulli's equation for such type of a isothermal process. You should remember all these derivations from the point of exam. Then adiabatic process. If we consider adiabatic process, only change P by rho raised to K is now constant, and let's say it is C2. So what you will get next? Rho raised to K is equal to what? Rho raised to K is equal to P by C2. So rho is equal to P by C2 raised to 1 by K. The next procedure will be same, that is the integration dou P by rho is equal to integration dou P divided by what it will be, P by C2, P by C2 raised to 1 by K. Or we rewrite it C2 raised to 1 by K, P raised to 1 by K into dou P. Let's take C2 raised to 1 by K out, and integration will be 1 means dou P divided by P raised to 1 by K. Or C2 raised to 1 by K integration P raised to minus 1 by K dou P. So what will be the answer? C2 raised to 1 by K into what? P raised to minus 1 by K plus 1 divided by minus 1 by K plus 1. So this is P raised to. So making further simplification, C raised to 1 by K, C2 raised to 1 by K into P raised to K minus 1 upon K divided by K minus 1 upon K, which is nothing but K upon K minus 1 into C2 raised to 1 by K into P raised to K minus 1 upon K. So all together, next, what you will get, which is equal to, further simplification, K upon K minus 1 into P upon, now replacing by C2. What is mean by C2? C2 is nothing but P upon rho raised to K. P upon rho raised to K raised to 1 by K into P raised to K minus 1 upon K. अजून पुढे K into K minus 1 P raised to 1 by K upon rho raised to K multiplied by 1 by K, making inside into P into K minus 1 upon K. So what will happen? Rho will get cancelled. Here K and K will get cancelled. So what you will get further? K into K minus 1 P, overall P is nothing but 1 by K plus K minus 1 upon K, correct, divided by rho, taking this and this together, these two. Altogether what you will get? K upon K minus 1 into P by rho, because what will happen? This 1 and this 1 will get cancelled. So K upon K, this K, everything will, P only will remain. K upon K minus 1 into P minus rho. So what you have got here, it is nothing but integration dou P by rho. So putting that value in the Bernoulli's equation, what you will get? K into K minus 1 P by rho plus V square by 2 plus GZ is equal to constant. So dividing by G, what you will get? K into K minus 1 P by rho G plus V square by 2G plus Z is equal to constant. So this is second equation of Bernoulli's for the adiabatic process. So you have to remember this first equation for isothermal and the continuity equation which we have derived, this for compressible flow. So these points you have to remember for the point of examination. These derivative, because there are no any problem based on such a compressible flow. You should remember what is meant by compressible flow, the derivation of all these. You don't have other derivations. These two derivations are important. Then one last point from the compressible flow is the properties which are called as what is mean by Mach number, what is mean by subsonic flow, sonic flow. These definitions are the last point. These are some last points from this compressible flow that I will share with you. Just a bit. So the concept is, next concept is called as a Mach number. It is again definition MACH, Mach number. It is nothing but it is square root of ratio of the inertia force of a flowing fluid to the elastic force. Means M is nothing but under root of inertia force. As we saw in the dimension analysis, same concept is here. It is a non-dimensional equation, and it is nothing but equation inertia force. Inertia force is given by rho a v square divided by elastic force is given by Ka. What you will get finally, under root v square upon K upon rho. It is just rearrangement which you should remember. V upon under root K by rho, or further V upon C, where C is nothing but under root K by rho, and that is nothing but Mach number, where V is velocity and C is known as a velocity of sound in the fluid in which we are considering. So Mach number is nothing but a ratio of velocity of fluid or body moving in the fluid. Velocity of fluid or body moving in fluid. So it is nothing but Mach number. This Mach number defines the flow. Flow, which is called as a subsonic flow. Subsonic flow means Mach number is less than 1.0. M is less than 1.0. Or we call it as a M is less than 1. Which means velocity of flow is less than velocity of sound. Velocity of flow is less than velocity of sound. Then there is a sonic flow, where we call it as a Mach number is equal to 1.0. Means velocity of flow is equal to the velocity of sound. Means V is equal to C. Here V was less than C. V is equal to C. It is sonic flow. Then supersonic. Supersonic flow means what? Here Mach number is greater than 1.0. Means V is greater than C. Velocity is greater than velocity of sound of wave. In the flow, we will call it as a supersonic flow. So you might have heard supersonic aeroplanes, supersonic velocity having the property of supersonic. Like that, it comes from the condition of this compressible flow. Concept is called as a Mach number. Mach number is nothing but it is a ratio of square root of inertia force to the square root of elastic force. So with this, we are concluding our unit number 5. As this compressible flow was the smallest part. Just a minute. See, uh, before we leave, as we know, you have to enter the roll numbers. What we have to know now, the unit number 5, what we have learned. So first point was forces on immersed body. In that, drag, lift, problems, blub body, streamline body. These were the points. And generation of lift on aerofile. And in second part, compressible flow. Just today, just now, we saw these all concepts. Remember, the fifth and sixth unit will have more weightage in the end semester exam. And you know, fifth unit is smallest unit as compared to the all 6 units. So it will have limited type of questions available. Remember, this chapter will have only few types of problems, few types of derivations. So make this unit number 5 perfect from the point of end semester exam. Then from next lecture, we will start unit number 6, which will be little bit lengthier. It will take almost 4 to 5 lectures to complete. And in upcoming week, we have to wind up this unit number 4, which is related with pumps and turbines. So with this, we will conclude today's session with Happy Makar Sankranti Vishesh. And you can add your roll numbers in the chat box as attendance, proof of attendance, only roll number, not other things. Today we have not taken any quiz that we will conduct based on this. In the next lecture, first we will start with the learnings from previous lecture on Padlet. Then we will have small quiz, and then we will continue with the unit number 6, that is unit number last. As you enter, you can view so that I will understand you have entered your number. If there is any doubt, you can unmute, speak. I will be here for a few minutes. You can ask any doubt in between in the chat box or by making unmute yourself. You might have seen the exam timetable in the group.